Consider the function with the rule g of x equals 2 plus the square root of x plus 4 over its maximal domain. The graph of y equals g of x is shown. For part A, we're asked to find g of -1 and the set of values of x such that g of x equals 6. So if we start with part 1, we have g of -1, and that simply tells us to substitute -1 in for x into the expression. So we have 2 plus the square root of -1 plus 4, which is equal to 2 plus the square root of 3. The square root of 3 can't be simplified, so that is simply the answer to part 1 for this question. For part 2, we're going to let g of x equal 6. So therefore, we're going to solve the equation 6 is equal to 2 plus the square root of x plus 4. Subtracting 2 from both sides will give 4 is equal to the square root of x plus 4. And then to solve for x, we're going to square both sides to get rid of the square root sign. So therefore, we want 16 to equal x plus 4. And the final step will be to subtract 4 from both sides, which will give us our answer x equals 12. So that is the answer to the second part of this question. For part B, we're asked to state the domain and the range of the function g. So the domain is all of the x values that are allowed inside this rule when we're considering the maximal domain. So we can base this off our graph and we can see that the smallest x value is -4, and that's included because it's got a square bracket. So it's going to be -4, and then the function goes off to infinity in the x direction. So that is the domain of the function g. We now need to consider the range of the function g, and this time we're going to look at the y values. So we can see that the smallest y value is 2, and that's included because of the square bracket. So it goes from 2, and once again it approaches positive infinity. So that is the range for the function g. For part C, we're asked to explain why the inverse function g -1 exists. And to have an inverse function, we know that the original function must be 1-to-1, which is exactly what this graph shows us. So g inverse exists because g is 1-to-1. So that is the response that we need to give for part C of this question. For part D, we're asked to fully define, by giving the rule and the domain, the inverse function. So to do this, the first thing we're going to do is we're going to let y equal g of x. So therefore we simply have the equation y equals 2 plus the square root of x plus 4. And now the second thing we're going to do is we're going to swap x and y to find the inverse. So therefore we have the equation x is equal to 2 plus the square root of y plus 4. The third thing we need to do is solve for y. So we can start by subtracting 2 from both sides of the equation, and we get that x minus 2 is equal to the square root of y plus 4, and then we can square both sides of the equation to progress towards getting y by itself. So therefore we have x subtract 2 all squared is equal to y plus 4, and the final thing we need to do to solve for y is subtract 4 from both sides of the equation. So therefore we can write y is equal to x subtract 2 all squared minus 4. However, we need to express this using the correct notation. So step 4 is to express using correct notation, and that will include giving the domain, which we're also asked to give in the question. So this function is now g inverse, such that the domain, which was the range of the original function g, so if we just write that out there, we have the domain of g inverse is equal to the range of the original function g, and the range of the original function g was simply 2 to infinity, which we found on one of the previous slides. So coming back to expressing this using correct notation, we have g inverse has a domain of 2 to infinity, which maps to the real number system for the rule g inverse of x is equal to x subtract 2 all squared minus 4. So that is the answer we needed to give for part D of this question. For part E, we're asked to show that the point of intersection between the function g and its inverse is at the coordinate 5, 5. So there's 3 equations you can solve to find the point of intersection. The first, which is usually the hardest, is when the function is equal to its inverse function's rule. The second equation is when you have the function is equal to x. And the reason this works is that the inverse function is a reflection over the line y equals x, so any points of intersection between g and its inverse will also be along the line y equals x. The third way we can find it is by going g inverse of x equals x. So we're actually going to explore options 2 and 3. So option 2 is when g of x is equal to x. So for this question, that would be 2 plus the square root of x plus 4 is equal to x. Subtracting 2 from both sides will give the square root of x plus 4 is equal to x subtract 2. And now we're going to square both sides to get rid of that square root sign. So therefore the left hand side will just be x plus 4 is equal to, and the right hand side we need to expand as a binomial expansion. So we get x squared minus 4x plus 4, not just x squared plus 4, which is a common mistake that a lot of people would make. And now we're solving a quadratic equation for x. So what we need to do is get all terms on one side. So we're going to subtract x plus 4 from both sides. So we're going to have 0 is equal to x squared minus 5x. And then subtracting 4 from both sides would just give plus 0. So that's all we'd have. So we can use the null factor law after we've factorised. So taking x out as a common factor, we're left with x times x minus 5. So therefore x equals 0 or x equals 5 are solutions to this equation. However, we know there was a domain restriction where we had x is greater than or equal to 2 as the domain. So therefore x equals 5 is the x value of that intersection point. And because it lies along the line y equals x, then if x is 5, y is also 5. So we'll also look at option 3 on this slide as well. And that's where we have g inverse of x is equal to x. So based on the rule for the inverse that we found before, we have x take 2 all squared minus 4 is equal to x. And now we're going to expand that quadratic term, which is going to give x squared minus 4x plus 4 minus 4 equals x. The plus 4 and the minus 4 would cancel to be 0, and we could subtract x to get the polynomial equal to 0. So therefore we have x squared minus 5x equals 0. So that's the same quadratic that we solved before, so we factorise x out as a common factor, leaving behind x subtract 5 is equal to 0. So the null factor law says that x equals 0 or x equals 5. Once again, we come to this same conclusion that x must be greater than or equal to 2 due to the domain that we'd already discovered in the previous parts of this question. So therefore only x equals 5. And as the points of intersection occur along the line y equals x, we find that the point of intersection must be 5, 5. So that is the answer we were asked to show in this question. Finally, for part F, we're asked to sketch the graph of y equals g inverse of x on the same grid, and we're asked to clearly label any axial intercepts, endpoints, and points of intersection with their coordinates. So the inverse of a function is a reflection over the line y equals x, so this point at negative 4, 2 would now be at 2, negative 4, so that's that point there at 2, negative 4. And the point at 0, 4 would now be at 4, 0, so that's that point there at 4, 0. And we found, or were asked to show, that the point of intersection was at 5, 5. So we also know that that point there at 5, 5 is also on the inverse function. If we do this in red, that inverse function g negative 1 is that parabola for the appropriate domain 2 to infinity as shown by the red graph now.